All right, page 27. Any questions, first of all? I know that there's page 26. The Newton's law of cooling is a little bit strange, so let me come back to that a little bit later. But other than that, any other questions from yesterday's homework that you guys had? So I want to still talk about differential equations for a little bit, and then I'd like for us to review the final topic under the AB course, which is area volume. So I want to review finding area, this method, washer method, cross section, and top minus bottom, right minus left. So just want to do a full review of that. But let me start off with this verifying solution for differential equations. These types of problems show up on AP exam multiple choice. And it's not hard. It's just you kind of have to get used to, this this line of reasoning. So for this one here, let's look at this together. It says the function e to the 3x minus 5x plus 7 is a solution to which of the following differential equations? And so we basically have to find y double prime and y prime for our function and kind of insert them into these choices and see which one of them will produce a true statement. Okay. So go ahead and try that. See if you can find y prime, see if you can find y double prime, and then use those pieces to help you decide, okay, which of those combinations will allow me to produce a true statement. So after you find y prime and y double prime, it is a little bit of kind of trial and error in terms of, okay, if I put this in here, am I going to get everything to cancel out? I just want everything to zero out. So which of those options will help me zero out my equation? What you guys get? A, yeah. So y prime is e to the 3x times 3 minus 5. Y double prime is 9 e to the 3x. And we just tested those options. The only one that's going to allow me to get a 0 at the end is going to be answer choice A. I think number one, bottom half is just solving your differential equation. So there's nothing unique about that. Number 4, can we try number 4 and 5? I just want to kind of get us a little bit more acclimated to page 29 of these types of questions. But really, you're just finding what they're asking for and then just solving for your missing value. So page 29, number 4. So treat K like you would like a 2 or 3. So if you just find y double prime, insert into that second equation, you should be able to solve for K. the problem is a little bit algebraically long, but really we're just taking our y prime or y double prime, inserting into that second equation, and then algebraically trying to figure out a way to move things around and get that k to give us a number. Okay, any questions? Replace y prime with our second derivative, replace y with our original equation, and then trying to combine all the like terms, try to get all the k terms together on one side, everything else on the other, and divide both sides and solve for k. Okay, any questions? All right, let me review area and volume. So let me do a little bit of review first, and then we'll look at page 35 and 36. Okay. Hey, I didn't print this out for you. Maybe I can make this formula sheet available so you can kind of see all the different formulas here. So with area, we're either doing top minus bottom or right minus left. So for instance, if I want to find the area between two graphs, I'm just going to draw one representative rectangle. And then I can just identify the top and the bottom, subtract it, and then my bounds are in terms of x as well. I'm basically adding infinitely thin rectangles from one end to the other, and there is no squared. It's just top graph minus bottom graph. Meanwhile, if I had two graphs that were neither of them are functions and they're both in terms of y, then I can do right minus left. And right minus left would be both equations in terms of y. So for instance, maybe this could be like an x equals, 4 minus y squared. And this could be x equals y squared plus 2. And then we can just do right curve minus left curve. If we want to do right minus left, everything has to be in terms of y, which means our equations will look like x equals on the left side, and our bounds are also in terms of y. So we'll get some practice with area. This method, this is where we're rotating around either a vertical or horizontal axis. And the way you can tell whether something is this method versus washer method is you look at your shaded region and see if the boundary of your shaded region is a flat surface, and that flat surface is up against your axis of revolution. Right? If you see your shaded region up against your axis, that means there's no gap. If there's no gap, then all we need is to build one radius. And the radius is always going to be perpendicular to your axis. Your axis and your radius will always intersect at a T. Next up, if I have a washer method, this is where there's either a gap or a hole or a curved region up against a dotted line. So for instance, let's say I had a shaded region that looked like this, and I'm rotating around an axis that it may be touching the axis, but if it's not a flat surface, there's a gap. If there's a gap, we have to draw two radius. One radius is extending from the axis to the furthest boundary, and the other is from the axis to the closer boundary. And that will be big R squared minus little r squared. For this method, we're adding infinitely thin circular disks. For washer method, we're adding infinitely thin circular rings. Cross sections are ones where we have a base and we're building different shapes on top of that base. So it could be a square, it could be a isosceles right triangle, it could be a rectangle, it could be different variations of triangle, it could be a semicircle. But essentially, the base, the shape of the base doesn't really matter. But we're always going to be told how to draw that base, whether it's a vertical or horizontal base. So if it's a vertical base, they will say something like parallel to the y-axis or perpendicular to the x-axis. If we see that, then we're going to be drawing a vertical base, a vertical base length. So we're going to treat it like area. We'll do top minus bottom, and then we'll take that base length and we'll insert it into whatever shape we're trying to build, either a square, triangle, or semicircle. But if a phrase says parallel to the x-axis or perpendicular to the y-axis, then that indicates that we want to draw a base length that's horizontal. And if we want to draw a base length that's horizontal, then we have to get our everything in terms of y. So anytime you see a horizontal base or horizontal radius or horizontal rectangle, you know you have to spend the time to rewrite your equation, get it in terms of x equals. Typically, the equations given to you are good for top minus bottom, but they're not quite ready for right minus left. Okay, so page 35. Let R be the region in the first quadrant bounded by the x-axis and the graphs of y equals natural log and phi minus x. Natural log is going to be the graph that's curved. The phi minus x is going to be the linear graph. Find the area of R. So if we want to find the area of R, there's two ways that we can do this. Let's explore doing top minus bottom first. So I think this is good practice for us to attempt two different variations so we can kind of be familiar with both ways. So if I want to do top minus bottom, meaning that I want to use vertical rectangles, I'm adding infinitely thin rectangles from one end to the other. And let's say this is one representative rectangle. Is this rectangle going to hit all the graphs that I need from one end to the other? if we want to do top minus bottom, what do we need to involve as well? Is there a different relationship elsewhere? Yeah, there is a different top graph, right? Different top graph with the linear versus the natural log. So we'll do top minus bottom here from 1 to wherever this intersection is. That'll give us the area of this first region. And then we'll need to do top minus bottom for the second region. Okay. So for this region, you can go from 1 to wherever this intersection is. And then for the other one, you can go from the intersection to whatever this x value is, which is 5. Okay. All right, try that. So see if you can use your calculator, find those intersection. Go ahead and write the x and y values for your intersection, because we're going to try part A using right minus left as well. But let's see top minus bottom first. So these representative rectangles, I think, are helpful because they're basically touching the graphs that we want to involve in our formula. So the top of my rectangle is sitting on the natural log of x. So that's the top graph for my left region. The bottom of my rectangle length is sitting on the x-axis. That's y equals 0. That's the bottom. And then I'm adding these infinitely thin rectangles that extends from this end all the way to here. My intersection is 3.693. And then separately, this triangle region, I'm going to find the area of that. So my bounds, the top of my rectangle is sitting on the 5 minus x. The bottom is sitting at the 0. Now, you could leave the zeros out. I'm just showing you that 0 just to show that I'm following the formula. But if you leave the zeros out, it's not an issue. It's just not, not every bottom function will be the x-axis. It's just for this problem it is. Let's do right minus left for this region as well. Obviously, on the AP exam, they're not going to ask you to do both ways. You can choose which way you want, but I think the right minus left is good practice for us to, for later on when washer and disk method may force us into a right minus left. So let's just see how that is different. So I'm going to So now we're going to think of it as adding infinitely thin rectangles in this orientation from the lowest y value to the highest y value. But anytime you see a horizontal base or length or rectangle or radius, you know these equations are not need to be adjusted. These are not in the proper form for us to use. So the y equals 5 minus x needs to be rewritten. So now this linear equation is going to be x equals 5 minus y. And then for the natural log of x, I can exponentiate both sides. If I want to solve for x, raise both sides with e as the base. And so x is equal to e to the y. So my linear graph is the x equals 5 minus y. And my natural log graph is the x equals e to the y. So let's build our area, our region, right minus left. So the right endpoint of my radius, sorry, of my rectangle is sitting on the 5 minus y, minus my left endpoint, which is sitting on the e to the y, and then just dy. No squared. I see a lot of students wanting to put a squared here because later on we're going to see volume, and volume is pi r squared a lot. So sometimes when students go back to doing area, they feel like this is like there's something missing. Okay? But area is supposed to be simpler because it's just a two-dimensional calculation. It's not three-dimensional. So all it needs is just top minus bottom. And then the bounds, you see how everything's in terms of y? That means my bounds also have to be in terms of what? I need y values, right? So I can't use the 1, the 3.6, and the 5. Those are all x values. I need the y values. So I see for my shaded region, my lowest y value is 0, and my highest y value is this intersection y value 1.3065. Part B, region R is the base of a solid, and we're building squares on top of the solid. So imagine this as lying on a flat surface, and we're going to be building squares that comes out of it. But we also have to make sure that we're in the proper orientation. We want perpendicular to the x-axis. So which direction is that? Vertical, yeah. So basically, we can reuse this diagram here. We know that we need two separate vertical relationship or setups here because there's two different graphs here in this region. So we'll treat this like a separate problem from this. So we'll do a cross-section formula for this region. We'll do a cross-section formula for this region, and then we'll just ultimately add them together. Okay. So with cross-section, we build it one dimension at a time. So we do top minus bottom. We kind of start off the same way as area. We're just going to find that top minus bottom relationship here. So so the area, I'm going to call this area 1, the one on the left, is going to be, sorry, let me start off with base. Let me call this base 1. So base 1 is going to be the dimension here, or the relationship here, top minus bottom, which is natural log of x minus 0, which is just natural log of x. I'm going to take that base and update it to the, or upgrade it to the area. So area for a square, right? We have different shapes here. It could be a square, it could be an equilateral triangle, it could be a semicircle. But the formula for a square is just base squared. So now I'm going to update my area to be natural log of x squared. Let me find out information about base 2, because we have a different region with that linear graph after, or that linear curve after the intersection. So for this one, the base is still vertical, right? Top minus bottom. The top is sitting at the 5 minus x. The bottom is sitting at the 0. My area, I still want squares. So still base squared. So now I put it all together, right? Once you have the area, then the third dimension is easier. You're just putting an integral around it, so you can accumulate from one end to the other. So my volume is the integral from, same as part A, 1 to 3.693. My base squared. And then separately, I'm going to find the interval from 3.693 to 5. That is sitting under the 5 minus x graph. It just asks us to write but not evaluate, so that means we can leave our answer in just the setup form. Part C says the horizontal line y equals k divides R into two regions of equal area. Write but do not solve an equation involving one or two or more integrals whose solution gives the value of k. We're going to reuse the information that we built from part A here. So let me draw that diagram again, but a lot of it we can reuse. So it says, imagine there's a horizontal line that is dividing the area in half. Some y equals k. And it's probably not going to be halfway, because it looks like the area below is greater than, it's a wider region below than above. So the line is probably going to be on the lower end. But we don't have to solve for k. We just have to create an equation that will potentially help us solve for k. So what we can do is we can say this. We can say, well, let's find the area, right? The area is 2.986. And they want us to do this horizontal orientation. So we can do right minus left, just like how we did before. So what if we did this? We can say, okay, wherever that line k is, we know that from 0 to k of these infinitely thin rectangles, phi minus y minus e to the y dy. We know that this is going to account for how much of the area? Half. So half of the area. We know the area is 2.986. So we've created an equation that can potentially help us solve for k. We don't have to solve for it. We can say, okay, wherever from 0 to k, wherever k is, this region is going to produce half the area. We can also say from k to 3.693, sorry, k to 1.3065. 17. Thanks. Okay, I want to do this method and washer method real quick before end of class. So page 36. Can we try B and D? Notice that I do have a flat surface here, but my dotted line is clearly off of that shaded region. So there's a gap. And because there's a gap and we're rotating around an axis, we know it's going to be washer method. So start at your dotted line, extend to the furthest boundary. That's going to be your big radius. And then start at dotted line, extend to your closer boundary. That's going to be your small radius. Part D, let's say the shaded region is rotated around the line x equals -1. But if I have a vertical axis, well, first off, it is still washer method. But I need to rewrite my equation because anytime I see a horizontal radius or length, my equations that's given to me are usually not going to be suited for us to use. So for here, everything's in terms of x. I can go from left bound to right bound. But here, everything's in terms of y. So my bound is in terms of y. Okay, so if we can finish the remainder of the packet for homework, page 27 to 36, I'll send out a reminder this afternoon. All right, come get your funds. For Thursday. Can you just send me pictures? Yeah. Thanks. Thank you.
That's a great question. It's Friday after spring break, right?